So once you get the idea, they mostly go the same way. Figure out if it's a simple or complex shape. But and then use one of the two formulas. They all have sort of their own quirky little things. So I decided to do number 52 as sort of a last example, and then there's nothing left to do but just sort of struggle with them. So number 52 says we want the area shared by the circles r equals 1 and r equals 2 sine theta. All right, so one thing we need is I don't know what r equals 2 sine theta looks like. I mean, maybe I could figure it out, but I don't feel like it. So we'll go to our y equals. We want r equals 1 and r equals, wait, this is number 52. Could have done this ahead of time, but I didn't. 2 sine theta, so just 2 sine theta. So it seems like it's probably a simpler problem, although, sometimes that's just deceptive. All right, so here's the graph, and I see a circle and another little circle. They're so cute. Each of these circles has radius 1. You can sort of, play around with the zoom and see what it really looks like, but basically they are two circles with radius 1. So what you have is this circle and this circle. And you are supposed to find the area that is shared, which is this area in here, the shared area. Now, arguably, this would be easier to do using rectangular coordinates, maybe. But then, one of the things about rectangular coordinates is that the equation of this circle becomes y equals plus or minus the square root of 1 minus x squared, right? Whereas polars is just r equals 1. So would it be easier? I don't know. Anyway, so let's look at it. One thing we're clearly going to need is these two intersection points. All right, so if I want to find those intersection points, then I need to solve where 2 sine theta equals 1. And remember, your calculator is not going to help you. You go calc and where's intersect? It does not have it. Sorry. All right, so that means you have to solve it. 1 equals 2 sine theta. Fortunately, it's not too hard. So we have 1/2 equals sine of theta. And then this pen is dying. And then, so yeah, I would go, it's theta equals inverse sine of 1/2, but I would think about unit circle. So if the sine is 1/2, then we're here, we're here. So this is pi over 6, this is 5 pi over 6, and those are the first two times that sine of theta is equal to 1/2. There's no argument in here for me to worry about, so just these intersection points are theta equals pi over 6, and theta equals 5 pi over 6. All right. Now, so I was thinking about, can we just do this circle minus this circle? But they aren't really the beginning and end. If you think radially, you have to think radially like this. This is how, the sections are going. So I found it helps to look at sort of a blow up of this. So let's look at a larger version where I have the 2 sine theta. Actually, this is the r equals 1, right? Nuts. Okay. R equals 1, and then here I have r equals 2 sine theta. So, and we know that this is pi over 6, and this is 5 pi over 6. All right, so what I think we have to see going on here is that the origin is here. So until we get to this theta equals pi over 6, the area is only controlled by one function, all right? The ends, these segments, if you think again about this beginning and end of the segment, the beginning of the segment is the graph r equals 2 sine theta. The end of the segment is 0. So for this whole part of the integral from theta equals 0 up to theta equals pi over 6, that integral is just the integral of the 2 sine theta function. So the area of that part is 1/2 the integral from 0 to pi over 6 of 2 sine theta squared, and it's d theta, and it's not a complex region because only one function controls the end of the segment. Now, what happens when we're going, here's the other intersection point over here, all right? So what happens when we're going in here? Well, we could do the integral from pi over 6 to 5 pi over 6 of 1 squared, right? But look, that's just a circle radius 1, and the angle of that sector is pi over 2, right? So it's an arc of pi over 2 from here to here. right? Because 5 pi over 6 minus 1 pi over 6 is 4 pi over 6, pi over 2. So the arc is pi over 2. So what I really have here is a quarter of a circle with radius 1. All right? So that is 1/4 of a circle with radius 1. That's what that blue part is. Right? It's just 1/4 pi r squared. So because there's no, the function is simple. It's just a circle. All right? Now, but then I have the other part over here where I go from 5 pi over 6, and I guess this is going to go to pi. All right, so I'm going to have then plus 1/2 the integral from 5 pi over 6 to pi of, now I'm back to using the 2 sine squared theta function, the 2 sine theta, right? So this is 2 sine theta here, and this is 2 sine theta here. So I'm back to using 2 sine theta squared. All right, with the 1/2, because 1/2 r squared d theta. All right, now I made a further simplification. I said, okay, but look, this part and this part are the same. So why don't I combine them together? And since each one is a half, we'll just make it 1. And I can either use 0 to pi over 6 or 5 pi over 6 to pi. Which one do you want to use? Let's use 0 to pi over 6. Okay, I'm losing the 1/2 because I'm putting 2 halves together. All right, integral of 2 sine theta squared d theta. And then the blue bit is just pi over 4, so plus pi over 4. So basically, like, all these shapes need an individualistic treatment of, you know, the analysis of what makes up the shape, and therefore what the area is going to be. So let's go ahead and do this, you know, finish this out. We need math 9 as our integral. We're doing 0 to pi over 6, so 0 to pi over 6, and we're doing 2 sine theta squared, 2 sine theta. You know, make sure you get your parentheses together here and get them in the right places and the right number. D theta. Enter, and I get 0.181, but I got to add the pi over 4, so plus pi over 4. I could have put that in at the beginning, but I basically forgot it. 0.96657. We'll call it 0.967, AP free response style. All right, there you go. You know, here's this area that we can break up this way. Here was an area that was between two shapes, so we did r2 squared minus r1 squared, but we were able to break up the petals and just do like 8 segments. So look for ways you can simplify using symmetry. You know, and this one was just a simple shape, our very first one. All right, just 1/2 the integral of r squared. So all you really have here is 2 formulas, right? This one and this one, and that's it. And there's really nothing else you can do with these except struggle with trying to do them yourself. So to that end, you are now assigned page 558. Look, I only gave you 5 problems because I want you to really think about them, okay? Really think about these 5 problems and give me correct answers, okay? Fully justified correct answers. Of course, fully justified just means you write the integral. Don't try to evaluate the integrals by hand, please. I mean, you can if you really, really want to, but please don't. All right? Write the integral, you know, with any fancy schmancy stuff. You know, sometimes the justification, like the justification is this solving for the intersection points, showing a diagram that shows why I wrote that integral, right? Why did I write this integral? Why did I put this 8 here? This is not a very good justification because I didn't draw the whole graph. That, you know, like this is pretty sketchy. I would let you get away with it. All right. But, you know, I carefully solved out the equation, got the limits, and wrote the integral. So, you know, make a nice sketch, show how you got the limits, right? Show how you got the limits, and then just evaluate on the calculator. Get them all right, do them carefully and thoughtfully, and that's it for the week.